are witnessing the acceleration of an impeller into cavitation as perceived by the naked eye through the transparent housing in a closed water loop. Cavitation occurs in a hydraulic system when the static pressure at any point in the fluid is lowered sufficiently to permit the liquid to rupture and form vapor-filled cavities. These cavities grow rapidly in regions of low static pressure and collapse violently upon entering high static pressure regions. Cavitation is of concern because it results in deterioration of hydraulic performance, physical damage, noise, and vibration. This study is limited to the first problem. This film presents a correlation between visual cavitation data and hydraulic performance parameters for these three mixed-flow impellers. The correlation parameters used in this study were head rise, flow rate, net positive suction head, and suction specific speed. Net positive suction head is defined as the sum of the inlet static head and the inlet velocity head minus the vapor head of the fluid. Suction-specific speed is defined as the product of the shaft speed and the square root of the flow rate divided by the net positive suction head raised to the 3/4 power. These studies were conducted in a closed water loop test facility. The heat exchanger maintained the loop water at approximately 100 degrees Fahrenheit. The high-speed movies were taken with a Fastex camera, operating in excess of 7,500 frames per second. In addition, still photos were made with a Leica camera using a high-speed strobe attack. For each impeller, your attention is invited to observe the variations in 1, locations of the cavitation bubble formations, and 2, the shapes of the bubble formations. The locations and shapes of the cavitation formations are shown to vary with net positive suction head, head rise, degree of flow incidence, and degree of stall. It is noted that the fluid cavities we shall see may contain air which has come out of solution, as well as water vapor. The loop water was degassed to approximately 6 parts per million air content. The first impeller tested was the RI-7A. Its tip blade angle of 8 degrees was the lowest of those tested. The arrow indicates the condition at which the runs were made. Note that these operating points were all at positive flow incidence. The cavitation is localized on the suction surface near the tip leading edge of the impeller vanes. Cavitation now extends along the suction surface to the hub. Note the vortex at the tip of the leading edge. Here, the tip vortex extends into the vane channel. Also note the formation of tip vortices in the rear channel. Compared to the previous flow rate, at this value of net positive suction head, the cavitation now extends over a greater portion of the leading edge. The effect of higher positive flow incidence is evidenced by the increased depth of the cavitation bubble and tip vortex. Initial stalling of the impeller is characterized by the forward-swept cavitation cloud. At this greater value of positive flow incidence, the cavitation is more prevalent along the suction surface of the vanes. Compared to the previous flow rates at this value of net positive suction head, the cavitation bubble formations are more pronounced. The cavitation pattern is highly complicated by the impeller operating further into stall. Localized cavitation exists on both surfaces of the vane leading edge. Also, note the tip vortices in the rear channel. Note the tip vortex on the pressure surface and the increased cavitation in the rear channel. Cavitation now extends completely across the tip of the rear channel. The cavitation regions are indicated by arrows. Only small areas of cavitation exist at this highest value of net positive suction head. A large cavitation bubble exists on the leading edge, with a tip vortex extending into the vein channel. Smaller tip vortices exist in the rear channel. Note the cyclic nature of the rear channel cavitation at the trailing edge of the impeller vein. At this throttle setting, a side view of the rear channel was taken at twice the speed, and for the net positive suction head corresponding to a 12% drop-off in the impeller head rise. The cyclic nature and extent of the rear channel cavitation is more evident in the following still photographs with reference marks. Cavitation is estimated to be blocking 60% of the flow channel. Cavitation is indicated by arrows. Stalling is evident by the forward-swept cavitation cloud. Cavitation now extends completely across the tip rear channel. The localized cavitation is indicated by arrows. Note the interaction of the rear channel cavitation with the splitter veins. The tip vortex on the pressure surface near the leading edge is more pronounced. The cavitation does not extend completely across the rear channel to produce a deterioration of performance, as noted for the RI-6A impeller. The small cavitation formations are indicated by arrows. Localized cavitation exists on both surfaces of the vane leading edges, and also on the suction surface of the splitter vanes. Note the interaction of the rear channel cavitation with the splitter vanes. The leading edge cavitation appears unrelated to the rear channel cavitation. A loss of hydraulic performance has resulted from cavitation entering the splitter flow channel. The localized cavitation at the leading edge on the suction surface is indicated by arrows. Stall is evidenced by the forward-swept cavitation formations at the tip section. The cavitation is localized on the suction surface at this highest value of positive flow incidence. Note the disappearance of the forward-swept cavitation with the loss of hydraulic performance. The cavitation has entered both splitter flow channels. Incipient cavitation in pump impellers occurs at much higher values of net positive suction head than are generally associated with a drop-off in hydraulic performance. Better methods of detecting incipient cavitation are needed. There are several distinct patterns of cavitation in impellers corresponding to different values of flow incidence, static pressure gradients, and degree of stall. At some flow conditions, the leading edge cavitation appears quite unrelated to the rear channel cavitation. Performance deterioration is principally due to large choking cavitation formations in the rear channels of impellers, which are initiated by the tip vortices. The cavitation formations associated with loss of hydraulic performance are cyclic in nature, whereas the leading edge cavitation is more stable. Further studies of cavitation flow patterns are needed to evaluate other important variables, such as speed effects, scale effects, and fluid thermodynamic properties. More basic understanding of the mechanics of cavitation will lead to better control of the conditions at which loss of performance, physical damage, and noise and vibration occur.